All right, here we are with week 8, chapter 18. We're going to cover this in several videos with synthetics and then individual videos for proteins, carbohydrates, lipids, and DNA. So they're all kind of interrelated in the sense that they do make bigger molecules than we've seen in previous chapters. So first we're going to see what polymers are and what kind of different monomers they come from. We're also going to see that they can make two varieties of polymers, and that's addition polymers and condensation polymers. We'll also see how this interrelates to the human body when it comes to adding molecules together to make proteins, to make carbohydrates, and the reversal of that process through digestion. So the generic idea of this chapter is polymers. Polymers are large molecules that are made up of single units. Sometimes this is one unit, sometimes this is two, as is most of the case for this chapter. There's going to be, one is typical for addition polymers, two is typical for condensation polymers that we'll see coming up. So the monomer unit is just the repeating unit, and you're going to need to know the monomers for lots of different polymers for the homework and the exam. So you need to know what is repeating itself in any type of biological molecule or addition polymer, as is the case for a matching section. So when we say addition polymer, what we really mean is they're adding themselves together. So this idea of adding the same molecule to itself over and over and over and over again is exactly what we are looking for. And when we name them, we just add the word poly in front. So notice if we're going to make a polymer out of ethene, notice it's going to be polyethylene. And if we're going to be making something out of propene, which would be, instead of 2 carbons long, now 3 carbons long with a double bond, notice propene is still part of the name. We're just adding poly to the front when we have more than one. Chloroethene. So chloroethene, pretty easy to recognize that there's chlorine in it. Vinyl chloride is the old common name for what we now call chloroethene. So that older name is what actually takes precedent here when they call it PVC, polyvinyl chloride. That comes from vinyl chloride, or chloroethene is its newer name. When you think of Teflon, think of those letters. Again, you saw poly up here. Teflon is the actual DuPont coded name for their product that they sell. But it still gives you a clue about its name. Notice the TEF, that's tetrafluoro, right? And then the flow, again, represents fluorine. And then it's always part of some kind of ene, and that's how we add double bonds to make single bonds to hold them together. Even with your styrofoam, you have styrene, comes from styrene, but when you put more than one styrene together, we call it polystyrene instead of just styrene. Add air to that, and you get styrofoam. So one of the biggest and most common polymers is polyethylene. Polyethylene comes from ethene, specifically. It's about 13 billion tons. Unfortunately, over half of that is trashed and stuck in landfills, and it's going to last pretty much forever because it is a hydrocarbon, much like those fossil fuels that last millions of years. These are going to last, hundreds of thousands of years, more than likely. About 25% get burnt, and only about 20% gets recycled and reused, which is unfortunate. Because it is 13 billion with a B tons per year that are made for our trash bags and Ziploc bags and those kinds of things. When we make polyethylene from ethene, this has a mass of about 50,000 grams. So you can imagine if carbon has a mass of 12 and hydrogen has a mass of 1, hydrogen has a mass of 1 for every CH2 unit. So each one of these units down here, CH2s, that's 12 plus 2. 12 plus 1 plus 1. And we're adding up to 50,000, so that's big, and that's real big in this case. So the reality of this idea and how it works to put these together is if we have a double bond with addition polymers, double bonds can react together to make single bonds. So when we have these When we have these double bonds, what happens is there's there's two electrons. There's one pair of electrons that represents these electrons here, and that double bond that we would connect together in our previous chapters. These electrons are allowed to add to the next molecule, add to the next molecule, add to the next molecule. And then eventually somebody will come back and add to this molecule, and that's going to do, up to 50,000 times. So that's tens of thousands of times when we have those units of 14. So if we look at the original structure, we still have those 3 carbon units. But now what we've traded is the double bond for a new single bond. So now we have this new bond here, this new bond here, this new bond here, and this new bond here. So those up here are called monomers at the top. So this is a monomer. And then this down here would be the polymer. And this is how all addition polymers are made. They're just made in some kind of sequence. So you can imagine if this is ethene, this would be polyethylene because it's got 2 carbon units all the way through. Let's say, as we're going to see in a couple upcoming examples, let's say that instead of ethene, it was propene. So that just means we have an extra carbon, an extra methyl. That just means that in this polymer chain, we're going to have an extra methyl every time. And it doesn't really matter if we aim it up or down. I chose up because it looked less crowded. If we were to see that polyvinyl chloride example we had earlier, then we'd have a chlorine here, and then on the polymer chain we'd have a chlorine here, and a chlorine here. That would give a little bit of polarity that ethene and propylene would not have. And that's the basic idea behind polymers, is that they have a little bit of variation in their chains just based on the monomers that we use. Whether it's 4 fluorines to make it super resistant to attractions, because fluorine's the most electronegative atom, that's what makes Teflon so non-sticky. Or if it's just vinyl chloride here that's more, say, like rain jackets and so forth, vinyl records, vinyl, Halloween kinds of suits, and that kind of thing. So what we want to be aware of is you can change the monomer. So whether you use 2 electrons like we just showed you or 1 electron each way, it's kind of like a wiper blade. It just kind of waves to one side or waves to the other side as those electrons move. So they can happen through radicals, which is single electrons, or they can happen through lone pairs, or at least bonding pairs that we were showing for those double bonds. And those are the common ways to make ethylene and other types of addition polymers specifically. A few minutes ago we talked about vinyl chloride. Vinyl chloride is the addition of chlorine to ethene, so that's called chloroethene by its IUPAC name. But based on its common name of vinyl chloride, we get polyvinyl chloride. What's important about these is that they're going to have a little bit of polarity. Chlorine has a 3.0. Carbon has a 2.5. So what's important here is to realize that you're polar at this position. So basically every other carbon, you're going to have some polarity. And that's going to change your physical properties just enough to be now used as saran wrap instead of, say, garbage bags and so forth. If we replace 1 chlorine and add 4 fluorines, now we get tetrafluoroethene. We don't really need to number it because we're saturating the carbon with fluorines, so all numbers are basically fluorines in this situation. But now notice we have the biggest bully, and every single bond is superpolar, and fluorine on top of it doesn't share with anybody because it's the most electronegative. It wants electrons the most. So this is a perfect situation for a non-stick coating to put on a cooking pan or a baking pan, because carbon-fluorine bonds do not share with the brownies, with the cheeseburgers, with the French fries that you put into those kinds of pans, or whether they're for baking or for frying or for whatever. So very common non-stick coating when you use fluorine atoms. As we look at other examples like propylene and styrene, both of these hydrocarbon-based, propylene having now 3 carbons, given that prefix of prop. This is used in all of our medicine bottles. This is used in our those plastic ropes you see on playgrounds. They do get kind of degraded by the sunlight over time, so they get kind of bristly, can give you even splinters if they get enough of that UV light over time. But they can be very pretty colors. Styrene itself is very dense, but if we add air to it, it can make styrofoam, which is not dense at all because of the air inside. And styrene has that arene structure with a alkene outside of it, actually called styrene in organic chemistry. And then you can get red Solo cups and all those foam-like containers from restaurants and the supermarket and for coffee cups and so forth. So as we look at a new example, we see 1,2-dibromoethene. So notice this is an ethene. It has to be in order to be based on an addition polymer. So if we have an ethene, we can draw eth and ene. Eth is 2 carbons. Ene is double bond. When it says 1,2-dibromo, it just means first carbon, second carbon, first carbon, second carbon, and then bromine. So this is 1,2-dibromoethene, and it has 2 carbons, a double bond, and 2 bromines located at the first carbon and the second carbon. So it's a good review for the naming of our previous chapter. And much like before, what we're going to do is allow these electrons that represent the double bond, allow them to add to the next carbon, add to the next carbon, and again somebody will add to them. So what happens in that situation then is the alkene itself is now going to be alkane based. Those electrons that added are now going to be connecting those single bonds together, and this is how we make monomers into polymers. So here's our new bond that holds the monomers together into a polymer, and then those red ones would have been the old bonds, and they too have those bromines still attached. So it's a very similar process to what we showed before. And this is the idea behind making monomers into polymers. A hybrid kind of category for plastics and all these polymers we've been talking about is rubber. Rubber's kind of unique in the sense that it has a 4-carbon unit typically, and then it can have branches from it. But what's unique about it is when you have 2 double bonds, notice when you're adding to somebody else. So if you're using this pair of electrons to add to another branch, somebody's adding to you. This pair of electrons here is actually adding to the middle so that there's still a double bond left. And when you have this single, double, single, and then double, single, having this ability to have these double bonds in between gives you some stretch, gives you some elasticity. So this is where we get elastic for, our rubber bands, for our, waistbands and our clothing and so forth. Also what we get for, rubber duckies or even rubber tires. This ability to have single, double combinations of addition polymers, giving them that flexibility of having different bond lengths, different, kind of stretching properties. So pretty unique that you can just manipulate that polymer chain and get, vastly different properties. And then we get to condensation polymers, which we'll pick up into with a separate video.